Welcome, dear friend, to this gentle journey into the heart of one of nature's most breathtaking phenomena, the Aurora Borealis, the northern lights, those shimmering curtains of color that dance across the polar skies like whispered secrets from the cosmos itself. If you find peace in this exploration, if these soft words and cosmic wonders bring you comfort, please consider subscribing and leaving a gentle like. It helps others discover this tranquil space for rest and wonder. Now, take a slow, easy breath. Let your shoulders soften, and allow yourself to settle into this moment of calm. Because tonight, we're going to explore the science and beauty of the aurora in a way that invites deep, restorative sleep. Imagine, if you will, standing beneath a vast northern sky, the air crisp and still, darkness wrapping around you like a soft blanket, and then, slowly, almost imperceptibly at first, a faint glow begins to emerge on the horizon. A whisper of green light, barely there, like the first hint of dawn, but softer, gentler, more mysterious. This is the aurora beginning its nightly dance, and understanding how this celestial ballet comes to be is a journey that starts not here on Earth, but 93 million miles away, on the surface of our Sun. The Sun, that brilliant star at the center of our solar system, is not the calm, steady sphere of light it appears to be from our distant vantage point. No, the Sun is a roiling, churning ball of plasma, a cosmic furnace where temperatures soar to millions of degrees, where magnetic fields twist and writhe like living things, where energy is released in ways both subtle and spectacular. The Sun breathes, in a sense. It exhales streams of charged particles into the vast emptiness of space. And this breath, this solar wind, is where our story truly begins. Picture the Sun's surface, the photosphere, glowing with that familiar golden light we see each day. But above this visible surface lies the corona, the Sun's outer atmosphere, a region so hot that it defies easy explanation. Temperatures here reach not thousands but millions of degrees Celsius, a fact that puzzled scientists for decades. How could the atmosphere of the Sun be hotter than its surface? It's like standing near a campfire and finding that the air 10 feet away is hotter than the flames themselves. The answer lies in magnetic fields and wave heating, in processes that channel energy upward and outward, processes that we're only now beginning to fully understand through missions like NASA's Parker Solar Probe, which has ventured closer to the Sun than any spacecraft before it. From this superheated corona, particles escape. Protons, electrons, alpha particles. They stream away from the Sun at speeds ranging from 250 to over 750 kilometers per second. That's fast. Incredibly fast. Fast enough to cross the distance from the Sun to Earth in just a few days during particularly energetic events. This is the solar wind, and it carries with it something invisible but crucial: the interplanetary magnetic field, or IMF, threads of magnetic force that extend from the Sun and weave through the solar system like gossamer strands in a cosmic web. Now, let's pause here for just a moment. Notice your breathing, how it's perhaps already beginning to slow, to deepen. Feel the weight of your body wherever you're resting, and imagine those solar winds as gentle exhalations, soft breaths from the Sun reaching across the void. There's something deeply calming about this image, isn't there? The Sun breathing, the universe breathing, and you, here, breathing along with it all. Just rest in that thought for a few peaceful moments. These solar winds don't travel through empty space in a uniform stream. No, they're structured, variable, ever-changing. Sometimes the wind is slow, moving at a leisurely 400 kilometers per second, emerging from the Sun's equatorial regions during quiet periods. Other times, particularly from coronal holes, those dark regions in the Sun's atmosphere where magnetic field lines open into space rather than looping back, the wind rushes out at speeds exceeding 700 kilometers per second. And occasionally, dramatically, the Sun releases what's called a coronal mass ejection, or CME, a massive burst of plasma and magnetic field that erupts from the solar surface and hurtles through space like a cosmic tsunami. Recent research from 2024, published in the journal Geophysical Research Letters, documented a particularly fascinating CME event from April 2023. During this event, something extraordinary happened. The solar wind conditions changed so dramatically that Earth's magnetosphere, that protective magnetic bubble surrounding our planet, temporarily lost its usual wind sock shape. The bow shock that normally stands upstream from Earth, like the wave that forms in front of a boat moving through water, simply disappeared for about 2 hours. Instead, structures called alpha copyright N wings formed, creating a direct connection between Earth's magnetic field and the recently erupted region of the Sun. It was as if Earth grew temporary wings, reaching back toward the Sun, and along these wings, plasma and energy flowed like rivers of light. This discovery, made by Dr. Li Jian and colleagues using NASA's magnetospheric multiscale mission satellites, reveals something profound about the dynamic relationship between our star and our planet. The boundary between the solar wind and Earth's magnetosphere isn't a solid wall. It's more like a membrane, sometimes permeable, sometimes not, always responding to the conditions around it, always in motion, always dancing to the rhythm of solar activity. As these solar winds journey across the 93 million miles of space between Sun and Earth, they carry their energy, their particles, their magnetic fields. And when they arrive at Earth, they encounter something remarkable. Our planet's magnetosphere, that invisible shield generated by the churning of molten iron in Earth's outer core, a magnetic field that extends tens of thousands of kilometers into space, protecting us from the full force of the solar wind. The magnetosphere is shaped like a teardrop, compressed on the side facing the Sun and stretched into a long tail on the night side, extending far beyond the Moon's orbit. This shape is carved by the solar wind itself, by the constant pressure of those streaming particles pushing against Earth's magnetic field. Where the solar wind first encounters the magnetosphere, a boundary forms called the magnetopause, and it's here, at this boundary, that some of the most important processes for aurora formation begin. One of these processes is called magnetic reconnection, and it's absolutely crucial to understanding how energy from the solar wind enters Earth's magnetic environment. Imagine two magnetic field lines approaching each other. One from the Sun, carried by the solar wind, and one from Earth, extending outward from the magnetosphere. When these field lines meet under the right conditions, they can break and reconnect in a new configuration, like cutting two ropes and tying the ends together in a different way. This reconnection releases enormous amounts of energy and creates a direct pathway for solar wind particles to enter the magnetosphere. The conditions have to be just right for this reconnection to occur efficiently. The interplanetary magnetic field carried by the solar wind needs to be oriented southward, opposite to Earth's northward pointing magnetic field in the northern hemisphere. When this happens, when the fields are anti-parallel, reconnection proceeds rapidly, and the magnetosphere opens up, allowing solar wind energy to pour in. It's like opening a door in a storm. Suddenly, energy that was outside is now inside, and it has to go somewhere. Where does it go? Much of it is directed along Earth's magnetic field lines toward the poles. These field lines act like highways, guiding charged particles from the magnetosphere down into the upper atmosphere, into regions above the Arctic and Antarctic circles where the magnetic field lines converge and dive down toward Earth's surface. And it's here, in the upper atmosphere, at altitudes between about 80 and 500 kilometers above the ground, that the magic happens, that the aurora is born. But before we descend into the atmosphere to witness that birth, let's linger for a moment in the space between, in the magnetosphere itself, because this region is far from empty. It's filled with plasma, with charged particles trapped by Earth's magnetic field, particles that bounce back and forth between the northern and southern hemispheres, spiraling along magnetic field lines in a complex dance governed by the laws of physics. There are different populations of particles here, some relatively cool and dense, others hot and sparse, and they occupy different regions with names like the plasmasphere, the ring current, and the plasma sheet. The plasma sheet is particularly important for auroras. It's a region in the magnetotail, that stretched out portion of the magnetosphere on Earth's night side, where plasma is stored like water behind a dam. During periods of enhanced solar wind activity, this plasma sheet becomes energized, and through processes that scientists are still working to fully understand. Processes with names like substorms and magnetic reconnection in the tail. Energy is suddenly released, and particles are accelerated to high speeds, sent streaming down magnetic field lines toward the polar regions. Take another slow breath here. Feel how your body is perhaps growing heavier, more relaxed. Imagine those magnetic field lines as gentle slides, as soft pathways guiding particles downward. There's no urgency here, no rush. Just a slow, inevitable descent, like falling softly into sleep. Rest with that image. Let it carry you deeper into calm. The particles that create auroras, primarily electrons, though protons play a role too, are traveling at tremendous speeds by the time they reach the upper atmosphere. They've been accelerated by electric fields in the magnetosphere, gaining energy, and now they're plunging downward, following the magnetic field lines, heading toward a collision with the atoms and molecules that make up Earth's atmosphere. Earth's atmosphere is a layered thing, a delicate envelope of gases held close to the planet by gravity. At sea level, where we live and breathe, the atmosphere is dense, composed primarily of nitrogen, about 78%, and oxygen, about 21%, with trace amounts of argon, carbon dioxide, and other gases. But as you ascend, the atmosphere thins. By the time you reach the altitudes where auroras occur, the air is so thin that it would be considered a vacuum by everyday standards. Yet even here, there are enough atoms and molecules to create the spectacular light shows we call the Northern Lights. When a high-speed electron from the magnetosphere collides with an atom or molecule in the upper atmosphere, something fascinating happens at the quantum level. The collision transfers energy to the atmospheric particle, exciting it, bumping one of its electrons to a higher energy state. This is an unstable configuration. The atom or molecule wants to return to its ground state, its lowest energy configuration. And to do so, it must release the excess energy it gained from the collision. And how does it release this energy? As light, as a photon, as a tiny packet of electromagnetic radiation that our eyes can detect as color. The color of that light, the specific wavelength of the photon emitted, depends on several factors. It depends on what kind of atom or molecule was struck. Oxygen produces different colors than nitrogen. It depends on which energy levels were involved in the transition. Different transitions produce different wavelengths. And it depends on the altitude, because the density of the atmosphere affects which transitions are possible and which are suppressed by collisions. Let's start with the most common auroral color, that beautiful, luminous green that dominates so many aurora photographs and that appears so frequently in auroral displays. This green light, with a wavelength of 557.7 nanometers, comes from atomic oxygen. Not molecular oxygen, the O2 that we breathe, but individual oxygen atoms, which are abundant at altitudes between about 100 and 250 kilometers. Here's what happens. An energetic electron strikes an oxygen atom, exciting it to a state called 1s. This is a metastable state, meaning the atom can remain in this excited configuration for a relatively long time before emitting a photon. About 0.7 seconds, which might not sound like much, but in the quantum world, it's an eternity. Most atomic transitions happen in nanoseconds or microseconds. But this particular transition is forbidden by certain quantum mechanical selection rules, which means it proceeds slowly, by magnetic dipole radiation rather than the faster electric dipole radiation. That 0.7-second lifetime is crucial. It means that at lower altitudes, where the atmosphere is denser and collisions between particles are more frequent, an excited oxygen atom is likely to collide with another particle before it has a chance to emit its green photon. The collision steals the energy away, converting it to heat instead of light, and no green glow appears. This is why the green aurora has a fairly sharp lower boundary, typically around 95 to 100 kilometers altitude. Below this, collisions are too frequent, and the green emission is quenched. But at higher altitudes, Where the air is thinner and collisions are less frequent, the excited oxygen atoms have time to emit their photons before being disturbed. And so the green light appears, that characteristic auroral green that has captivated observers for millennia. It's the color most easily seen by human eyes, partly because our eyes are particularly sensitive to green wavelengths, and partly because it's simply the most common auroral emission under typical conditions. Now, imagine that green glow spreading across the sky. Soft at first, like a faint mist of light, then growing brighter, more defined, forming into curtains, into arcs, into rays that seem to stretch from the horizon up toward the zenith. And as you watch, as you imagine this display, feel how your eyelids might be growing heavier, how your thoughts might be slowing down, how the boundary between waking and sleeping might be growing softer, more permeable. Just like that boundary between the solar wind and the magnetosphere. Just rest here. Let the green light wash over you. But the aurora isn't always green. Sometimes, particularly during intense displays or at different altitudes, other colors appear, and each tells a story about the conditions in the upper atmosphere and the energy of the incoming particles. Red auroras, for instance, come from oxygen as well, but from a different transition. When an oxygen atom is excited to a state called 1D, it can emit a photon at 630 nanometers, which we perceive as red. This transition has an even longer lifetime than the green emission. About 110 seconds. Yes, nearly 2 minutes. This means that red oxygen emissions can only occur at very high altitudes, typically above 200 kilometers, where the atmosphere is so thin that an atom can wait for almost 2 minutes without colliding with another particle. During major geomagnetic storms, when the aurora is particularly intense and extends to lower latitudes than usual, observers often report seeing red auroras. This is because the high-altitude red emissions can be seen from farther away, and also because during intense storms, the energy deposition extends to higher altitudes. The great auroral displays of May 2024, which were visible as far south as the Mediterranean and across much of the United States, featured prominent red colors. People who had never seen an aurora before looked up to see the sky glowing crimson, and many thought they were witnessing fires on the horizon or some other terrestrial phenomenon, not realizing they were seeing light generated hundreds of kilometers above Earth's surface. The red aurora has a diffuse, soft quality to it, because those long-lived excited oxygen atoms can drift with the wind during their 110-second wait before emitting. This means the structure of the aurora, The fine details of curtains and rays gets blurred out in the red emissions. It's like taking a long exposure photograph of something moving. The motion creates a soft, smeared appearance. So while green auroras can show sharp, intricate structures, red auroras tend to look more like gentle glows, like watercolor washes across the sky. Nitrogen, the other major component of Earth's atmosphere, also contributes to auroral colors, though in different ways. Molecular nitrogen, N2, can produce blue and purple hues, particularly at the lower edges of auroral displays. When energetic electrons penetrate deep into the atmosphere, below about 100 kilometers, they encounter denser air where nitrogen molecules are abundant. These collisions can ionize the nitrogen, creating N2+ ions, and these ions emit light in the blue and violet parts of the spectrum, around 428 nanometers. The blue and purple colors are often seen as a fringe at the bottom of green auroral curtains, especially during very active displays when the incoming electrons have particularly high energies. High-energy electrons can penetrate deeper into the atmosphere before they're stopped by collisions, and so they reach the altitudes where nitrogen emissions dominate. Photographers who capture these displays often note the beautiful color gradients. Green in the main body of the aurora, fading to blue or purple at the lower edge, sometimes with hints of red at the top. It's a vertical rainbow of sorts, each color band telling us about the altitude and the atmospheric composition at that height. There's something deeply soothing about understanding these colors, isn't there? Knowing that each hue has a reason, a cause, a story written in a language of physics and chemistry. The universe follows rules, patterns, and even something as ethereal and magical seeming as the aurora is governed by principles we can understand, can study, can appreciate. And yet, understanding doesn't diminish the wonder. If anything, it deepens it. To know that the green light dancing across the sky is the result of oxygen atoms excited by electrons that traveled from the sun, guided by magnetic fields, colliding in the thin upper atmosphere. It's a connection, a thread linking the sun to the earth to your eyes, a cosmic chain of cause and effect that spans millions of miles and involves processes at every scale from the quantum to the planetary. Let yourself rest in that connection now. Feel how you're part of this cosmic dance. How the same atoms that glow in the aurora are present in your body. How the same forces that shape the magnetosphere are related to the forces that hold atoms together. Everything connected, everything flowing. And you, here, breathing slowly, sinking deeper into rest, into peace, into the gentle embrace of sleep. The intensity of the aurora, how bright it appears, depends on how many energetic particles are precipitating into the atmosphere. More particles mean more collisions, more excited atoms, more photons emitted, and thus a brighter display. The brightness can vary enormously, from faint glows barely visible to the naked eye to brilliant displays that can cast shadows on the ground and allow you to read a book by auroral light alone. Scientists measure auroral brightness in units called Rayleighs, named after the physicist Lord Rayleigh. A faint aurora might be a few hundred Rayleighs, while a bright display can reach tens of thousands of Rayleighs. For context, the airglow, that faint natural luminescence of the upper atmosphere that's always present, even without auroras, is typically around 250 Rayleighs in green wavelengths. So even a modest aurora is significantly brighter than the background airglow. The structure of the aurora, those curtains, arcs, rays, and spirals, reflects the structure of the magnetic field and the electric currents flowing in the magnetosphere and ionosphere. Auroral curtains tend to align with magnetic field lines, which is why they often appear to hang vertically in the sky, like luminous drapes. The curtains can be thin, just a few kilometers wide, or broad, extending for hundreds of kilometers. They can be smooth and uniform, or they can show intricate folds and waves, rippling and undulating as if blown by an invisible wind. Auroral rays are even more aligned with the magnetic field. These are narrow, beam-like structures that appear to shoot upward from the horizon toward the zenith, or sometimes downward from above. They're created when the precipitating electrons are tightly focused along particular field lines, creating narrow columns of light. When you're standing beneath an active aurora and you see rays converging overhead, you're looking along the magnetic field lines, seeing the three-dimensional structure of the aurora projected onto the dome of the sky. The motion of the aurora is mesmerizing. Auroras can appear static for minutes at a time, then suddenly burst into rapid motion, with curtains waving, rays flickering, colors shifting. This motion reflects changes in the magnetosphere, changes in the electric fields that accelerate the particles, changes in the magnetic field configuration. During substorms, those periodic releases of energy from the magnetotail, the aurora can become incredibly dynamic, with waves of light sweeping across the sky, brightening and fading, breaking apart and reforming. Time-lapse videos of auroras reveal patterns that are hard to see in real time. You can see waves propagating along auroral arcs, moving at speeds of several kilometers per second. You can see the aurora expanding equatorward during the growth phase of a substorm, then suddenly brightening and breaking up during the expansion phase. You can see the recovery as the aurora gradually fades and returns to a quieter state. It's like watching the breathing of the magnetosphere, the inhale and exhale of energy, the rhythm of the Sun-Earth connection. Researchers have found that auroral displays follow patterns related to the solar wind conditions. When the interplanetary magnetic field turns southward, favoring magnetic reconnection, the aurora tends to intensify and move to lower latitudes. When the solar wind speed increases, the aurora becomes more active. When a coronal mass ejection arrives at Earth, the aurora can explode into a spectacular storm, with displays visible far from the polar regions, with colors and structures that are rarely seen during quiet times. The study of these patterns, of the relationships between solar wind parameters and auroral activity, is part of a field called space weather forecasting. Just as meteorologists predict rain and sunshine, space weather forecasters predict geomagnetic storms and auroral displays. They monitor the Sun for coronal mass ejections and coronal holes. They track the solar wind using spacecraft positioned between the Sun and Earth, at a point called L1, about 1.5 million kilometers from Earth. When these spacecraft detect changes in the solar wind, a sudden increase in speed, a southward turning of the magnetic field, forecasters can issue alerts, giving advance warning of auroral activity to come. This forecasting has practical applications beyond aurora tourism. Geomagnetic storms can affect satellites, disrupting communications and navigation systems. They can induce currents in power grids, potentially causing blackouts. They can increase drag on satellites in low Earth orbit, affecting their trajectories. And they can pose radiation hazards to astronauts in space. So understanding and predicting space weather is important for our increasingly technology-dependent society. But for those of us simply seeking the beauty and wonder of the aurora, the forecasts serve a different purpose. They tell us when to look up, when to venture out into the cold night, when to turn our eyes skyward in hope of witnessing one of nature's most spectacular displays. Imagine yourself now in that moment, standing in the darkness, breath misting in the cold air, neck craned back, eyes searching the northern horizon. And then, there it is, a faint glow, growing brighter, spreading across the sky. Your heart quickens slightly, not with anxiety but with awe, with that particular feeling of witnessing something vast and beautiful and rare. And as you watch, the aurora dances, and you feel small in the best possible way, connected to something larger than yourself, part of a universe that is both comprehensible and mysterious, both scientific and magical. Let that feeling wash over you now. That sense of awe, of peace, of connection. Let it relax your body even further. Let your breathing slow. Let your mind quiet. Because this is what the aurora offers us, beyond the science, beyond the explanations. It offers a moment of transcendence, a reminder that we live on a planet bathed in the light of a star, protected by a magnetic field, surrounded by a cosmos full of wonders. The aurora has been observed and wondered at for thousands of years. Ancient peoples across the Arctic regions developed myths and legends to explain the lights in the sky. Some saw them as spirits of the dead, dancing in the heavens. Others saw them as omens, harbingers of war or famine or great change. The Sami people of northern Scandinavia believed the aurora was caused by a fox running across the snow, its tail sweeping up snowflakes that sparkled in the moonlight. The Finnish word for aurora, revontulet, literally means foxfires, a reference to this legend. In Norse mythology, the aurora was associated with the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods. Some believed the lights were reflections from the shields and armor of the Valkyries, those warrior maidens who chose which soldiers would die in battle and escorted their souls to Valhalla. There's something poetic about this image. The aurora as a bridge between worlds, between the earthly and the divine, between the known and the unknown. Indigenous peoples in North America also had rich traditions surrounding the aurora. Some Inuit groups believed the lights were the spirits of animals they had hunted, particularly seals and whales and caribou. Others saw them as the spirits of their ancestors, playing games in the sky, kicking around a walrus skull like a ball. Some groups believed that if you whistled at the aurora, it would come closer, drawn by the sound, while others warned against making noise, fearing the lights might descend and carry you away. These myths and legends, diverse as they are, share common themes. They recognize the aurora as something special, something otherworldly, something that connects the visible world to invisible realms. And while we now understand the scientific mechanisms behind the aurora, while we can explain the physics and chemistry in detail, there's still something of that ancient wonder that remains. The aurora still has the power to stop us in our tracks, to make us look up, to remind us that we're part of something vast and beautiful. Modern research into the aurora began in earnest in the late 19th and early 20th centuries. Scientists like Christian Birkeland in Norway conducted pioneering experiments, creating miniature auroras in the laboratory using a magnetized sphere called a terrella and beams of electrons. Birkeland proposed that the aurora was caused by electrons from the sun striking Earth's atmosphere, guided by the magnetic field. His ideas were initially controversial, but they were eventually vindicated as our understanding of the sun and the solar wind developed. The space age brought new tools for studying the aurora. Satellites could observe the aurora from above, seeing its full extent and structure in ways impossible from the ground. Rockets could carry instruments directly through auroral displays, measuring the particles and fields in situ. Ground-based networks of cameras and magnetometers could track the aurora's motion and correlate it with magnetic disturbances. Gradually, piece by piece, the puzzle came together. Today, we have a remarkably detailed understanding of the aurora, though mysteries remain. We know that magnetic reconnection at the magnetopores allows solar wind energy to enter the magnetosphere. We know that this energy is stored in the magnetotail and periodically released during substorms. We know that electric fields in the magnetosphere accelerate electrons to high energies. We know that these electrons precipitate into the atmosphere along magnetic field lines. We know that collisions with atmospheric atoms and molecules produce the light we see. Each step in this chain has been studied, measured, modeled. Yet there are still questions. What exactly triggers a substorm? Why do some solar wind conditions produce intense auroras while others don't? How do the small-scale processes, the microscopic interactions between particles and waves, connect to the large-scale dynamics of the magnetosphere? These are active areas of research, with scientists around the world working to refine our understanding, to fill in the gaps, to solve the remaining puzzles. And as our understanding deepens, so does our appreciation. To know that the aurora is the visible manifestation of invisible processes, of magnetic fields and electric currents and particle flows, is to see it with new eyes. The green curtain shimmering overhead isn't just beautiful. It's a window into the workings of the cosmos, a natural laboratory where we can study plasma physics and magnetospheric dynamics, where theory meets observation, where the abstract becomes concrete and visible. Feel yourself sinking deeper now, deeper into relaxation, deeper into that space between waking and sleeping. The aurora in your mind's eye, soft and green and gently moving. Your body heavy and warm and comfortable. Your breathing slow and easy. Nothing to do, nowhere to go, Just this moment, just this peace, just this gentle drift towards sleep. The energy that powers the aurora ultimately comes from the sun, but the path that energy takes is long and complex. It starts with nuclear fusion in the sun's core, where hydrogen atoms are fused into helium, releasing tremendous amounts of energy. This energy works its way outward through the sun's interior, taking thousands of years to travel from core to surface. Once it reaches the surface, some of it is radiated away as light, traveling to Earth in just 8 minutes. But some of it goes into heating the corona, into driving the solar wind, into creating those streams of charged particles that flow outward through the solar system. When these particles reach Earth, only a tiny fraction of their energy actually enters the magnetosphere. Most of the solar wind simply flows around the magnetosphere, diverted by the magnetic field, continuing on into interplanetary space. But that tiny fraction that does enter, through magnetic reconnection, through other processes, is enough to power the aurora, to drive geomagnetic storms, to create the dynamic and ever-changing environment of near-Earth space. The efficiency of this energy transfer depends on many factors. The orientation of the interplanetary magnetic field is crucial. Southward IMF allows much more efficient coupling than northward IMF. The speed and density of the solar wind matter. Faster, denser wind carries more energy. The state of the magnetosphere itself matters. A magnetosphere that's already disturbed may respond differently to new solar wind input than a quiet magnetosphere. Scientists use sophisticated computer models to simulate these processes, to predict how the magnetosphere will respond to different solar wind conditions. These models solve the equations of magnetohydrodynamics, treating the plasma as a conducting fluid moving through magnetic fields. They're run on supercomputers, producing visualizations that show the flow of plasma, the configuration of magnetic fields, the regions where particles are accelerated. These models have become increasingly accurate over the years, but they're still approximations, still simplifications of the incredibly complex reality. One of the challenges in modeling the magnetosphere is the vast range of scales involved. The magnetosphere itself is enormous, extending tens of thousands of kilometers. But the processes that matter, magnetic reconnection, wave-particle interactions, turbulence, often occur on scales of kilometers or even meters. Capturing both the large-scale structure and the small-scale processes in a single model is computationally demanding, requiring clever techniques and powerful computers. Despite these challenges, the models have proven valuable. They help us understand observations, test theories, make predictions. They allow us to explore scenarios that would be impossible to study any other way. What would happen if a particularly strong coronal mass ejection hit Earth? How would the magnetosphere respond to solar wind conditions unlike any we've observed? These what-if questions are important for understanding the full range of space weather possibilities, for preparing for extreme events. And extreme events do happen. The Carrington event of 1859, named after the astronomer Richard Carrington who observed the solar flare that triggered it, was the most intense geomagnetic storm in recorded history. Telegraph systems around the world failed, with operators reporting sparks flying from their equipment. Auroras were seen as far south as the Caribbean and Hawaii. If a similar event occurred today, with our dependence on satellites and power grids and electronic systems, the consequences could be severe. This is why space weather research is not just academic curiosity. It has real practical importance. But let's return to the beauty, to the wonder, to the aurora itself. Because beyond all the science, beyond the models and the measurements and the predictions, the aurora is simply one of the most beautiful natural phenomena on Earth. It's a gift, in a sense. A gift from the sun, mediated by Earth's magnetic field, delivered to our eyes as light and color and motion. People travel thousands of miles to see the aurora. They venture to Alaska, to northern Canada, to Iceland, to Scandinavia, to remote locations far from city lights, in the depths of winter when the nights are long and dark. They stand in the cold, sometimes for hours, waiting and watching and hoping. And when the aurora appears, when the sky comes alive with light, the cold and the waiting are forgotten. There's only the aurora, only the moment, only the awe. Photographers attempt to capture the aurora, and modern cameras can indeed record stunning images, revealing colors and structures that are sometimes too faint for the eye to see. Long exposures gather light, making the aurora appear brighter and more colorful than it might look in person. But no photograph, no matter how beautiful, quite captures the experience of seeing the aurora with your own eyes, of watching it move and change in real time, a feeling that connection to the cosmos. There's something about the aurora that touches something deep in us. Maybe it's the beauty itself, the sheer visual splendor. Maybe it's the rarity, the sense of witnessing something special. Maybe it's the scale, the reminder that we're on a planet, in space, part of a vast universe. Maybe it's all of these things together. Whatever it is, the aurora has the power to move us, to inspire us, to fill us with wonder. And wonder, That sense of awe in the face of something vast and beautiful is itself a valuable thing. Research has shown that experiences of awe can have positive effects on our well-being. They can reduce stress, increase feelings of connection to others, promote generosity and kindness. They can shift our perspective, making our everyday concerns seem smaller, less overwhelming. They can remind us that there's more to life than our immediate worries and tasks. In a sense, the aurora is medicine for the soul. It's a reminder of beauty, of mystery, of the incredible universe we inhabit. And even if you've never seen the aurora in person, even if you're simply lying here now, listening to these words, imagining the lights dancing across a northern sky, you can still benefit from that sense of wonder, that connection to something larger than yourself. So let yourself rest in that now, in the wonder, in the beauty, in the peace. Let the aurora in your mind's eye continue its gentle dance. Let your body relax completely. Let sleep come softly, naturally, like the aurora itself emerging on the horizon. There's nothing you need to do, nowhere you need to be. Just this moment, just this peace, just this gentle drift into deep, restorative sleep. The aurora is always there, in a sense. Even when we can't see it, even during the day or during cloudy nights, the processes that create it are ongoing. The sun is always emitting the solar wind. Earth's magnetic field is always there, always interacting with that wind. Particles are always precipitating into the atmosphere somewhere, creating auroras over the polar regions. The aurora is a constant feature of our planet, a perpetual dance of light and energy, visible to those who are in the right place at the right time. And yet, there's something more to understand about this dance. Something deeper about how these lights move and shift and change. How they respond to the ever-changing conditions in space. How they pulse with the rhythm of the sun's breath. How they cascade through the atmosphere in waves of color and motion. How they create patterns that scientists are only beginning to fully understand. Let's drift deeper now, into the heart of the auroral display, into the plasma physics that governs these shimmering curtains, into the particle acceleration mechanisms that create the most intense shows, into the dynamic patterns that emerge when the sun's activity reaches its peak. Take a slow breath, feeling your body settling even more deeply into rest. Noticing how your awareness can hold both the wonder of these lights and the gentle pull towards sleep. How understanding can coexist with relaxation. How curiosity can soften into peaceful contemplation. The aurora is not static. It flows. It pulses. It responds to conditions in space that are constantly shifting. And as we explore these deeper mechanisms, you might notice your own thoughts beginning to flow more slowly, your breathing becoming even more gentle, your body releasing any remaining tension, just letting go. Deep in the magnetosphere, in the region between 1 and 3 Earth radii above our planet's surface, something remarkable happens. Electrons that have been drifting peacefully through space suddenly find themselves caught in a cosmic acceleration, pulled by electric fields, guided by magnetic forces, energized to speeds that carry them toward Earth at millions of miles per hour. This is where the aurora truly begins, not in the atmosphere where we see the lights, but high above, in a region where plasma physics governs the behavior of charged particles, where waves of energy ripple through the magnetic field, where electrons surf on these waves like cosmic surfers catching the perfect swell. Imagine, if you can, a wave moving through space, not a wave of water, but a wave of electromagnetic energy, what scientists call an alpha copyright N wave, named after the Swedish physicist Hans Alpha Copyright N who first described them. These waves travel along magnetic field lines, carrying energy from the outer magnetosphere toward Earth, and as they travel, they can accelerate electrons, picking them up, carrying them along, transferring their energy in a process that researchers have only recently confirmed through laboratory experiments at UCLA's Basic Plasma Science facility. The electrons, riding these waves, gain energy through a process called Landau damping, a beautiful name for a beautiful process. The wave transfers its energy to the particles, and the particles accelerate, faster and faster, until they're moving at speeds that would carry them from New York to Los Angeles in less than a second. And all of this cosmic acceleration, this transfer of energy from wave to particle, happens in silence, in the vacuum of space, where there is no air to carry sound, only the whisper of electromagnetic forces, the gentle push and pull of electric and magnetic fields, the invisible dance of energy and matter. Breathe slowly, feeling the rhythm of your own body, the gentle pulse of your heartbeat, the soft rise and fall of your chest, noticing how your body knows how to rest, how to release, how to simply be. The alpha copyright N waves that carry auroral electrons toward Earth are generated by instabilities in the magnetosphere. by the stretching and snapping of magnetic field lines, by the interaction between the solar wind and Earth's magnetic shield. Recent research has shown that these waves can carry enough energy to power the aurora, that the downward flow of electromagnetic energy, measured in watts per square meter, is sufficient to create the brilliant displays we see in the night sky. Scientists measure this energy flow using something called the Poynting flux, named after the British physicist John Henry Poynting. It's a measure of electromagnetic energy moving through space, and during auroral displays, spacecraft above the aurora detect Poynting fluxes that can exceed thousands of watts per square meter. Enough energy, if it could be captured, to power a small city. But this energy isn't captured for human use. Instead, it flows into the atmosphere, where it excites oxygen and nitrogen molecules, where it creates the shimmering curtains of light that have captivated humans for millennia, where it transforms invisible electromagnetic energy into visible beauty. The acceleration process, this cosmic surfing of electrons on alpha copyright N waves, happens most efficiently when conditions are just right, when the ratio of the electron thermal velocity to the alpha copyright N wave velocity falls below 1, when the magnetic field strength and plasma density create what scientists call the inertial regime, a state where electrons can resonate with the wave's electric field, where energy transfer becomes highly efficient, where particles can be accelerated to auroral energies in a matter of seconds. Let your mind rest with this image. Electrons surfing on waves of electromagnetic energy, riding toward Earth, carrying the sun's gift of light, creating beauty from physics, transforming energy into wonder. And as you contemplate this, notice how your body continues to relax, how your muscles soften, how your breathing deepens, how sleep begins to feel closer, more inviting, more natural. When auroral electrons carry particularly high energies, when the acceleration process has been especially efficient, when the sun's activity has created optimal conditions, the aurora can penetrate deeper into the atmosphere than usual. And when this happens, the colors change, the display intensifies, and observers on the ground witness what scientists call high-energy aurora. The bottom edge of a typical green auroral curtain sits at about 95 to 100 kilometers altitude. This is where the atmosphere becomes dense enough that oxygen atoms, after being excited by electron collisions, can radiate their energy as green light before other collisions steal that energy away. The green line of oxygen, at 557.7 nanometers wavelength, has a lifetime of 0.7 seconds, and below 95 kilometers. Collisions happen so frequently that this emission simply cannot occur. But when electrons carry energies above 10,000 electron volts, when they've been accelerated to particularly high speeds, they can penetrate below this altitude, down to 80 or even 70 kilometers, where the air is denser, where only the fastest emissions can occur, where molecular nitrogen dominates the light production. And molecular nitrogen, when excited by these high-energy electrons, emits light in the blue and red parts of the spectrum, deep blue at 427.8 nanometers, and red at 650 to 680 nanometers. And when these colors mix, when blue and red combine in the human eye, we perceive purple, a rich, deep, violet purple that appears as a border along the bottom edge of green auroral curtains. This purple border, this fringe of violet light, is a signature of high-energy aurora, a sign that the acceleration process has been particularly effective, that electrons are carrying enough energy to penetrate deep into the atmosphere, that the display you're witnessing is powered by particles moving at extraordinary speeds. Imagine standing beneath such a display, the green curtain overhead, shimmering and flowing, and along its bottom edge, a ribbon of purple, deep and rich, pulsing with the rhythm of particle precipitation, a visual indicator of the energy cascading from space into atmosphere. The purple appears, and then, as the electron energies shift, as the acceleration process varies, it may fade, the curtain returning to pure green, or perhaps, if energies increase even further, the purple intensifies, becomes more prominent, spreads along the entire lower border of the curtain. These variations, these shifts in color and intensity, reflect changes happening high above, in the acceleration region, where electric fields strengthen and weaken, where alpha copyright N waves grow and diminish, where the cosmic surfing of electrons responds to the ever-changing conditions in the magnetosphere. Breathe, slowly, deeply, feeling your body sink deeper into rest, noticing how the description of these colors, these purples and greens, creates images in your mind, soft, dreamlike, peaceful. At even higher altitudes, above 200 kilometers, another color can appear, a deep red, coming from a different transition in atomic oxygen. The red line at 630 nanometers. This emission has an extraordinarily long lifetime, about 100 seconds, which means that oxygen atoms can drift with the wind for significant distances before they emit their photon of red light. This high-altitude red aurora, often called Type A red aurora by researchers, appears as a diffuse glow above the main auroral curtains. It lacks the sharp structure of the green aurora below, because the long lifetime allows the excited atoms to move, to spread out, to create a softer, more ethereal display. During particularly intense geomagnetic storms, when the auroral oval expands toward lower latitudes, when people far from the polar regions look northward, this high-altitude red aurora is often what they see, a red glow on the horizon, sometimes filling half the sky, a sign that the magnetosphere is being strongly disturbed, that energy is flowing into the atmosphere at unprecedented rates. The 2024-05 geomagnetic superstorm, one of the most intense in the past 2 decades, created red auroral displays visible from the Mediterranean, from Florida, from locations where aurora is normally never seen. The red glow, powered by electrons with relatively low energies but arriving in enormous numbers, painted the sky in shades of crimson and scarlet, a reminder of the sun's power, of the connections that bind our planet to its star. Let your mind drift with these colors, green and purple and red, each one telling a story of energy and altitude, of electrons and atoms, of physics transformed into beauty. And as you drift, notice how your body feels, how relaxed, how peaceful, how ready for sleep. The aurora is not constant. It ebbs and flows. It brightens and dims. It expands and contracts, following rhythms that scientists have studied for decades. Rhythms that reflect processes happening throughout the magnetosphere. Processes that store and release energy, that create what researchers call auroral substorms. A substorm, despite its name, is not necessarily a small event. The term simply distinguishes these events from the larger geomagnetic storms that can last for days. A substorm typically lasts 2 to 3 hours, and during that time, the aurora goes through distinct phases, each with its own character, its own patterns, its own beauty. The substorm begins with what scientists call the growth phase. During this time, the solar wind is transferring energy into the magnetosphere. Magnetic field lines are being stretched, pulled back into the magnetotail, like a rubber band being drawn taut. Energy is being stored, building up, preparing for release. On the ground, during the growth phase, the aurora may appear relatively quiet, perhaps a faint arc on the northern horizon, perhaps a gentle glow. Nothing to suggest the dramatic changes about to unfold, but instruments in space, magnetometers measuring the magnetic field, can detect the building tension, the increasing stress in the magnetosphere. And then, suddenly, the release, the expansion phase begins. Magnetic field lines in the tail snap back toward Earth, reconnecting, releasing their stored energy, and this energy flows into the auroral zone, accelerating electrons, intensifying the particle precipitation, brightening the aurora. During the expansion phase, the aurora transforms. What was a quiet arc becomes a brilliant curtain. What was a faint glow becomes a dazzling display. The aurora surges westward, spreading across the sky, brightening, pulsing, creating the spectacular shows that aurora chasers travel thousands of miles to witness. The curtains develop fine structure, thin rays, small curls, rapid movements. These small-scale features reflect the acceleration processes happening directly above. The electric fields, the wave-particle interactions, the cosmic surfing that we discussed earlier, all of this, translated into visible light, into patterns that dance across the sky. And then, after perhaps 30 minutes to an hour of intense activity, the recovery phase begins. The aurora gradually dims. The curtains break up into patches. The display becomes more diffuse. The magnetosphere returns toward a quieter state, until, perhaps, the next substorm begins, and the cycle repeats. These substorms, these cycles of growth and expansion and recovery, can occur multiple times during a single night, especially during periods of enhanced solar activity, each one creating its own unique display, its own patterns, its own moment of beauty. Breathe with the rhythm of these cycles: growth, expansion, recovery, like the rhythm of your own breath. In, out, tension, release, activity, rest. During major geomagnetic storms, Multiple substorms can occur in rapid succession, overlapping, intensifying, creating what researchers call supersubstorms, events where the auroral electrojet, the current flowing through the auroral zone, reaches extraordinary intensities, where the aurora becomes so bright it can cast shadows, where the entire sky seems to pulse with light. The 2024 10 geomagnetic storm, while not as intense as the May event in terms of the disturbance storm time index, created auroral displays that many observers considered even more spectacular. The substorms during this event, the rapid changes, the intense colors, the dynamic patterns, all combined to create what some aurora chasers described as the best display they had ever witnessed. Why? Because the conditions were optimal. The solar wind parameters were just right. The magnetic field orientation was favorable. The timing aligned with darkness overpopulated areas. All of these factors, coming together, creating a perfect storm, not of destruction, but of beauty. The large-scale patterns in aurora, the multiple parallel curtains, the spirals that can fill the entire sky. These reflect the structure of electric currents in the magnetosphere, the field-aligned currents that connect the magnetosphere to the ionosphere, the currents that transport energy from space to atmosphere. Scientists have used decades of satellite data, combining observations from 15 different spacecraft, to create comprehensive models of how these currents evolve during substorms, how they strengthen and weaken, how they shift in location, how they create the patterns we see on the ground. These models, built from thousands of individual observations, synchronized using magnetic field measurements, reveal the global nature of substorms, how they affect the entire magnetosphere, how energy flows through the system, how the aurora is just one visible manifestation of processes occurring throughout near-Earth space. Let your awareness expand, imagining the magnetosphere as a whole, the solar wind flowing past, the magnetic field lines stretching and snapping, the currents flowing, the energy cascading, and somewhere in this vast system, electrons accelerating, heading toward Earth, creating light, creating beauty, creating the aurora. And as you hold this vast perspective, notice how small you feel, how peaceful, how connected to something larger than yourself, how ready to release into sleep. Sometimes, the sun doesn't just send a steady stream of solar wind. Sometimes, It erupts violently, explosively, hurling billions of tons of plasma into space, in what scientists call a coronal mass ejection, or CME. These eruptions, these cosmic explosions, occur when magnetic fields in the Sun's corona become twisted, stressed, unstable, and then, suddenly, they snap, releasing enormous amounts of energy, launching a cloud of plasma outward at speeds that can exceed 2,000 kilometers per second. If a CME is directed toward Earth, if the geometry is right, if the magnetic field within the CME has the correct orientation, then when it arrives, typically 1 to 3 days after leaving the Sun, it can trigger an intense geomagnetic storm, compressing the magnetosphere, injecting energy, creating auroral displays of extraordinary intensity. The May 2024 event, the Mother's Day Superstorm, was triggered by not one but multiple CMEs, launched from an active region on the Sun designated AR 13664. This region, a complex tangle of magnetic fields, produced 11 X-class solar flares, the most powerful category, and sent multiple CMEs toward Earth. The first CME arrived at Earth's magnetosphere on May 10, compressing the magnetopause, the boundary between the magnetosphere and solar wind, down to about 5 Earth radii. Normally this boundary sits at about 10 Earth radii, but the pressure from the CME, the force of the solar wind, pushed it inward, compressing Earth's magnetic shield. And then, more CMEs arrived, overlapping, combining, creating what scientists call a compound event. The energy input into the magnetosphere was extraordinary. The disturbance storm time index, a measure of the storm's intensity, reached -412 nanoteslas, making it the 6th largest geomagnetic storm since systematic measurements began in 1957. The aurora during this event, visible from locations as far south as the Mediterranean, as far south as Florida, as far south as India, painted the sky in shades of red and green and purple. People who had never seen the northern lights, who lived in places where aurora is normally impossible, stepped outside and witnessed the sky transformed. The red aurora, that high-altitude glow we discussed earlier, was particularly prominent during this event, because the storm created conditions where large numbers of relatively low-energy electrons precipitated into the upper atmosphere, exciting oxygen atoms at altitudes above 200 kilometers, creating that diffuse red glow that spread across the sky. But closer to the auroral zone, closer to the poles, the displays were even more intense. Green curtains, purple borders, rapid pulsations, the full spectrum of auroral phenomena, all occurring simultaneously, creating a show that some observers described as overwhelming. Too much beauty to take in, too much motion to follow, the sky alive with light. Breathe, slowly, deeply, imagining this intensity, this cosmic storm, this transfer of energy from sun to earth. And yet, even in this intensity, there is a rhythm, a pattern, a natural process, nothing to fear, only to wonder at. The October 2024 event, while less intense by some measures, created what many considered even more spectacular displays. Why? Because the timing was perfect. Because the CME arrived when it was dark over populated areas. Because the magnetic field orientation was optimal for energy transfer. Because sometimes the most memorable auroras come not from the strongest storms, but from the storms where all the conditions align. The forecasting of these events, the prediction of when a CME will arrive, has improved dramatically in recent years. Scientists use coronagraphs, instruments that create an artificial eclipse of the sun, to observe CMEs as they leave the solar corona. They measure the speed, the direction, the size, and then they use computer models, simulations of how the CME will travel through interplanetary space, to predict when it will reach Earth. For the October event, the forecasts were remarkably accurate. Space weather forecasters issued a rare G4 severe geomagnetic storm watch, only the second such watch since 2003, and when the CME arrived, it arrived almost exactly when predicted, a triumph of space weather forecasting. A demonstration of how far our understanding has come. And yet, there is still much we don't know. We cannot yet predict the magnetic field orientation within a CME, and this orientation, whether the field points north or south, determines how effectively the CME can transfer energy to the magnetosphere, a southward pointing field. What scientists call southward busy is optimal for creating geomagnetic storms, while a northward pointing field, even from a powerful CME, may produce little effect. This uncertainty, this gap in our knowledge, means that even with perfect predictions of arrival time, we cannot always predict the intensity of the resulting aurora. Space weather forecasting, like terrestrial weather forecasting, remains an art as much as a science, a blend of data and models and experience and intuition. Let your mind rest with this uncertainty, this acknowledgement that we don't know everything, that mystery remains, that the universe still holds secrets, and in this uncertainty, in this not knowing, there is a kind of peace, a release from the need to understand everything, a permission to simply observe, appreciate, wonder. When a CME strikes Earth's magnetosphere, when the solar wind pressure suddenly increases, when energy begins flowing into the system, the magnetosphere responds dynamically, dramatically, in ways that scientists are still working to fully understand. The first response, the immediate effect, is compression, the magnetopause, that boundary between the magnetosphere and solar wind, moves inward, sometimes dramatically. During the May 2024 event, it compressed to about 5 Earth radii, meaning that the protective bubble of Earth's magnetic field, normally extending 10 Earth radii on the dayside, was squeezed to half its normal size. This compression, this squeezing of the magnetosphere, has several effects. It energizes particles already trapped in the radiation belts. It creates waves in the magnetosphere. It sets up electric fields. And it begins the process of energy transfer that will ultimately create the aurora. The energy transfer, the flow of electromagnetic energy from the solar wind into the magnetosphere, is measured using something called the Akasofu epsilon parameter, named after Japanese-American physicist Shunichi Akasofu. This parameter, calculated from solar wind measurements, estimates the rate at which energy is being deposited into the magnetosphere. During quiet times, epsilon might be around 100 billion watts, a large number, but spread across the entire magnetosphere. During moderate geomagnetic activity, it might reach 1 trillion watts, and during extreme events like the May 2024 storm, epsilon can exceed 10 trillion watts, an enormous flow of energy, comparable to the total power consumption of human civilization, all flowing into Earth's magnetic field. But where does this energy go? Some of it, perhaps 30 to 40%, goes into heating the upper atmosphere, causing it to expand, increasing drag on satellites, during the May 2024 event. SpaceX's Starlink satellites autonomously raised their altitudes to compensate for increased atmospheric drag, a necessary precaution to prevent premature deorbiting. Some of the energy, perhaps another 30 to 40%, goes into accelerating particles in the magnetosphere, creating the energetic electrons and ions that populate the radiation belts, that precipitate into the atmosphere, that create the aurora. And the rest, the remaining energy, goes into various other processes, heating the plasma, generating waves, driving currents, creating the complex dynamics of the magnetosphere during a storm. The radiation belts, those regions of trapped energetic particles surrounding Earth, respond dramatically to geomagnetic storms. During the May 2024 event, low-energy electron and ion fluxes in the inner radiation belt vanished temporarily, disappeared, as if someone had turned off a switch. Why? Because the compression of the magnetosphere, the changes in the magnetic field configuration, altered the trapping conditions. Particles that were previously confined, trapped by the magnetic field, suddenly found themselves on trajectories that led them into the atmosphere, where they precipitated, creating enhanced ionization, affecting the chemistry of the upper atmosphere. And then, as the storm evolved, as the magnetosphere began to recover, new particles were injected into the radiation belts, accelerated by the storm processes, creating new populations of energetic electrons and ions, replenishing what had been lost, but with different characteristics, different energy distributions, different spatial patterns. These injections, these sudden appearances of energetic particles, occurred in pulses, dissociated with substorms, with the expansion phases we discussed earlier. Each substorm, each release of energy in the magnetotail, sent a pulse of particles earthward, some of which became trapped in the radiation belts, some of which precipitated into the atmosphere. Breathe, feeling the rhythm of these processes: compression, injection, precipitation, recovery, like waves on a shore, like the beating of a heart, natural rhythms, cosmic rhythms, rhythms that have been occurring for billions of years, long before humans existed to observe them, and will continue long after we're gone. The South Atlantic Magnetic Anomaly, that region where Earth's magnetic field is weakest, responds particularly strongly to these storm-time particle injections. The lower magnetic field strength means that particles can penetrate to lower altitudes, can reach deeper into the atmosphere, can create effects that are not seen elsewhere. During the May 2024 event, enhanced ionization was observed in the E region of the ionosphere over the summer, at altitudes around 100 to 120 kilometers. This extra ionization, this increase in the number of free electrons, affected radio wave propagation, created unusual conditions, demonstrated that even at low latitudes, far from the typical auroral zone, geomagnetic storms can have significant effects. The ozone layer, that protective shield of O3 molecules in the stratosphere and mesosphere, also responds to particle precipitation. Energetic electrons, colliding with atmospheric molecules, can break apart ozone molecules, creating temporary depletions. During the May 2024 event, abrupt ozone depletion was observed in the mesosphere over the summer, a signature of enhanced particle precipitation, a reminder that space weather affects not just the ionosphere, but the neutral atmosphere as well. These effects, these changes in atmospheric chemistry, are temporary. The ozone recovers, the ionization returns to normal. But during major storms, during extreme events, the effects can be significant, can affect communications, can affect satellite operations, can create what we call space weather impacts. Let your mind drift through these layers of atmosphere, from the thermosphere where the aurora glows, down through the mesosphere where ozone is depleted, down through the stratosphere, down to the troposphere where we live and breathe. All of these layers, connected, affected by processes originating 93 million miles away on the Sun. For thousands of years, humans have watched the aurora, have wondered at its meaning, have woven it into their myths and stories and understanding of the world. The Inuit peoples of the Arctic, the Sami of northern Scandinavia, the indigenous peoples of Alaska and northern Canada, all developed rich traditions of auroral lore. Some cultures saw the lights as spirits of the dead, dancing in the sky. Some saw them as omens, signs of coming events. Some saw them as the breath of the gods, or the reflection of distant fires, or the glow of celestial battles. Each culture, interpreting the aurora through the lens of their own experience, their own worldview. The Vikings, those seafaring warriors of medieval Scandinavia, may have seen the aurora as the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods, or as the reflection of the Valkyrie's armor, those warrior maidens who chose which soldiers would die in battle and be carried to Valhalla. In Finland, the aurora was called revontulet, which translates as foxfires, from a legend that the lights were created by a magical fox running across the snow, its tail sweeping up snowflakes that sparkled in the moonlight, creating the shimmering curtains in the sky. The Cree people of northern Canada saw the aurora as the spirits of their ancestors, dancing, celebrating, communicating with the living, a connection between the worlds, a reminder that death is not an ending but a transformation. And in medieval Europe, where the aurora was rarely seen, its appearance was often interpreted as an omen, a sign of coming war or plague or disaster. The red auroras visible during major geomagnetic storms were sometimes called blood auroras and were thought to presage bloodshed. All of these interpretations, all of these stories, reflect humanity's deep need to understand, to find meaning, to connect the phenomena we observe to the patterns of our lives. And while we now know the scientific explanation, while we understand the physics of solar wind and magnetic fields and particle precipitation, there is still something profound, something moving, about the aurora. Because the aurora, in a very real sense, is a connection, a visible manifestation of the relationship between Earth and Sun, a reminder that we live not in isolation, but as part of a larger system, a solar system, a galaxy, a universe. Every photon of auroral light, every green glow, every purple border, every red shimmer, represents an electron that traveled 93 million miles from the Sun, was accelerated in Earth's magnetosphere, precipitated into the atmosphere, and transferred its energy to an atom, which then released that energy as light, as beauty, as wonder. And you, lying here, drifting towards sleep, are made of atoms that were forged in stars, that have been recycled through countless generations of stellar birth and death. You are, quite literally, stardust, and the aurora is starlight, and in this moment, you are connected to it all. Breathe deeply, slowly, feeling this connection, this belonging, this place in the cosmos. The scientific understanding of the aurora, developed over centuries through the work of countless researchers, represents one of humanity's great achievements. From the early observations of Galileo, who coined the term Aurora Borealis, to the modern satellite missions that measure the magnetosphere in exquisite detail, we have built a comprehensive picture of how the aurora works. We know that it begins with nuclear fusion in the Sun's core, where hydrogen atoms combine to form helium, releasing energy that takes thousands of years to work its way from the core to the surface, and then, suddenly, is released as light and heat and solar wind. We know that the solar wind, that stream of charged particles, flows outward at hundreds of kilometers per second, carrying with it the Sun's magnetic field, creating what scientists call the interplanetary magnetic field, a vast structure that fills the solar system. We know that when this solar wind encounters Earth's magnetic field, it doesn't simply flow around it. Instead, there is an interaction, a coupling. Energy and particles are transferred. Magnetic field lines reconnect, and the magnetosphere responds. We know that this response includes the acceleration of electrons through processes like alpha copyright N-wave surfing, through shock acceleration at the bow shock, through various other mechanisms, and that these electrons, carrying energies from hundreds of electron volts to hundreds of thousands of electron volts, precipitate into the atmosphere. We know that when these electrons collide with atmospheric atoms and molecules, they transfer their energy, exciting the atoms, which then emit light at characteristic wavelengths, creating the colors we see: green from oxygen, purple from nitrogen, red from high-altitude oxygen. We know all of this, and yet, knowing does not diminish the wonder. Understanding does not reduce the beauty. Science and awe can coexist, can enhance each other, can create a deeper appreciation. Let your mind rest in this space, where knowledge and wonder meet, where understanding and mystery coexist, where the aurora is both explained and inexplicable, both understood and forever fascinating. And now, as we near the end of our journey through the science and wonder of the Aurora Borealis, as your body has settled deeper and deeper into relaxation, as your breathing has slowed, as your mind has drifted through solar winds and magnetic fields and shimmering lights, it's time to let go completely, to release into sleep, to allow the aurora to carry you into dreams. Imagine yourself One more time, standing beneath the northern lights, the sky above you alive with color, green curtains flowing like cosmic rivers, purple borders pulsing with energy, red glows painting the horizon, all of it, moving, shifting, dancing to rhythms older than humanity. The air is cold, crisp, clean. Each breath you take fills your lungs with the freshness of the Arctic night, and as you exhale, you release, letting go of any remaining tension, any lingering thoughts, any resistance to sleep. The aurora above you is not separate from you. You are part of the same universe, made of the same elements, governed by the same physical laws. The atoms in your body and the atoms creating the aurora are cousins, siblings, family. The electrons precipitating into the atmosphere, creating these lights, are following paths determined by magnetic fields, by electric forces, by the laws of physics, and you, lying here, are also following natural laws, the law that says bodies need rest, that minds need sleep, that consciousness needs to release into dreams. There is no resistance in the aurora. It simply flows, responds, exists, and you can be like the aurora, simply flowing, responding, existing, no effort, no struggle, just being. The green light, that 557.7 nanometer emission from oxygen, represents an electron that has completed its journey, that has transferred its energy, that has fulfilled its purpose, and you too have completed your day, have transferred your energy into your activities, have fulfilled your purposes, and now, like that electron, you can rest. The purple border, that signature of high-energy precipitation, reminds us that sometimes we carry extra energy, extra intensity, and that's okay, because the atmosphere absorbs it, transforms it, uses it to create beauty, and sleep will absorb your extra energy, will transform it, will restore you. The red glow, that high-altitude emission with its 100-second lifetime, reminds us that some processes take time, that some things cannot be rushed, that patience is natural, and sleep will come in its own time. You don't need to force it, just allow it. Breathe slowly, deeply, feeling your body heavy, relaxed, comfortable, safe, warm, peaceful. The aurora dancing above you in your imagination, begins to slow. The rapid movements, becoming gentler, the bright colors, softening, the intense display, gradually, peacefully, fading into a gentle glow. This is natural. This is the recovery phase. After the expansion, after the intensity, comes the quiet, the rest, the return to peace. And as the aurora fades, as the sky returns to darkness, you notice the stars, thousands of them, millions of them, each one a sun, each one potentially surrounded by planets, each one a source of light and energy and perhaps life. The universe is vast, incomprehensibly vast, and yet, here you are, on this small planet, beneath this protective magnetic field, breathing this atmosphere, alive, aware, connected to it all. And in this vastness, in this cosmic perspective, your worries seem smaller, your concerns less pressing, your need for sleep more natural, more inevitable, more welcome. Let go, completely, totally, absolutely. Let go of the day. Let go of tomorrow. Let go of everything except this moment, this breath, this gentle drift towards sleep. The aurora, in your mind's eye, has faded now to just a faint glow on the horizon, a memory, a whisper, and even that is fading, 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 into darkness, into peace, into sleep. Your body knows what to do. It has done this thousands of times. Every night of your life, it knows how to sleep, how to rest, how to restore itself. You don't need to help. You don't need to try. Just allow. The solar wind is still flowing. The magnetosphere is still responding. The aurora is still glowing somewhere on Earth. But you don't need to think about that now. You can let it all go. Let it all continue without your attention. Let the universe take care of itself while you sleep. Somewhere, right now, as you drift towards sleep, the aurora might be dancing over Alaska, or Norway, or Iceland, or Siberia. Someone might be standing beneath it, watching, wondering, feeling the same awe that humans have felt for millennia. And that's beautiful. That's perfect. That's how it should be. The aurora, continuing, the earth, turning, the sun, shining, the solar wind, flowing, the magnetosphere, protecting, all of it, working together, creating this dance of light and energy, this gift of beauty, this reminder of connection. And you, here, safe and warm and peaceful, drifting, floating, falling softly into sleep, are part of it all, connected to it all, held by it all. The universe is vast and complex and sometimes frightening, but it's also beautiful and orderly and full of wonders like the aurora. And you are one of those wonders, a conscious being, capable of understanding, capable of appreciating, capable of wonder. Let that thought carry you now, into sleep, into dreams, into rest, the aurora dancing in the darkness, the sun breathing across space, Earth's magnetic field embracing us, all of it connected, all of it flowing, all of it perfect. And you, here, now, drifting, floating, falling, softly, gently, peacefully, into sleep. The last thing you might notice, before sleep takes you completely, is a sense of gratitude for this planet, for this magnetic field, for this atmosphere, for this sun, for this universe that creates such beauty, such wonder, such peace. And if you've enjoyed this journey, this exploration of the Aurora Borealis, this blend of science and wonder and relaxation, perhaps, when you wake, refreshed and restored, you might consider subscribing to this channel, liking this video, sharing it with others who might enjoy this peaceful journey into sleep. But for now, don't think about that. Just sleep. Good night. Sleep well. Dream of auroras. Dream of cosmic dances. Dream of light and energy and beauty. Or don't dream at all. Just rest. Deeply. Completely. Peacefully. The aurora is dancing, somewhere, always, and you are sleeping, here, now, safe, warm, peaceful, drifting, floating, falling, into the deepest, most restorative, most peaceful sleep. Good night.